And it's nice to be here. Whoops, my computer's talking to me. So let me see. Whoops, don't want to do that. Hold it. Okay, here we go. It's supposed to start here. Oops, come on. Okay, I'm gonna have to restart this here. Okay, back. Oh, okay, I know what I'm gonna do. Now, good. You can tell I'm a little bit rusty here after I retired for about a year. Okay, good. So here we go. I'll record this just for my own benefit. Okay, so this is what I'm going to talk about. Let's start mostly about the Cassini mission to Saturn, which some of you have heard of and some of you have not. And I'm going to talk about the orbiter, an orbiter and a probe. And then I'm going to talk a little bit about Saturn's atmosphere. And I'm going to talk about the rings and what we call little moonlets, which are little objects that float around the rings. A couple of the satellites of Saturn, which are future NASA targets. Very interesting satellites, both of them. And I'll talk about that. And then I'll talk about the age and origin of the rings. So that's the general picture here. Those of you with telescopes are still familiar with the moon. And it's always amazed me that if you really were to be seeing Saturn next to the moon, you could actually see it. You get a good eye, almost. And if you've ever got that occultation that happened this summer, you can only see that. But that gives you an idea of its real apparent size in the sky. Of course, we know that Saturn is much further away than the moon, so the only reason it looks so big is so huge. Saturn is almost as big from edge to edge of the rings as from Earth to the moon. What? Yes, it's that big. Oh, and I want to encourage you guys, if anybody has a question along the way, because I can get going pretty fast, and just ask your questions. So I don't want to. And I've got things I can toss out at the end. Okay, so that's the real scale of things. We used to think back when I was in grad school 100 years ago that Saturn was, well, the big question was, why is Saturn the only giant planet with rings? It's the big question. And now we know, thanks to the Voyager spacecraft that I'll talk about, that it's not the only giant planet with rings. All the giant planets have rings. Jupiter has a ring. Uranus has a little sketchy ring. Neptune has some sketchy rings. So they all have rings, but only Saturn has these big, massive, bright white, majestic rings. All these other rings, all these other giant planets are kind of sketchy, hardly there, and the particles in them are very dark, like coal. Okay, so Saturn's rings are still unusual. It's still a puzzle, and I will get to that at the end. So what do we know? A little bit of an overview about Saturn's system. Here you can see the main, what we call the main rings, and the various divisions and gaps in the main rings. I'll talk about all these things. Some of the little moons that orbit near the edge of the rings. We call them mid-sized icy moons. These things are a couple hundred kilometers across. And this gives them all to their actual relative sizes.
Jeff, why do you call them icy?
Because they're mostly made of water ice. People say, oh, how weird. All these satellites made of water ice. It turns out water ice is one of the most common solids in the universe. It's not a surprise, and there's a reason that I can tell you traces back to nuclear physics and stars. But water ice is very common, and most of these are made out of water ice, as are the rings.
They don't need freezers.
Not there. Oh, no. Everything's frozen solid. So just for scale, here's this little moon I'm going to talk about called Enceladus. It's pretty small. Our moon is about yay big. Planet Mercury is about that big. Mars is about that big. And Saturn has this giant moon called Titan, which is somewhere between Mercury and Mars in size. So it's a planet-sized satellite. And it's a fascinating satellite that actually has an atmosphere, and I'll talk a lot about that later. So that gives you sort of a sense of scale about the things that we're talking about here. Okay, I should check the time. All right. Well, here's Voyager. Voyager was the first spacecraft to really open our eyes to the outer solar system. And I was actually, this is, you know, great spacecraft. Here's what we call the scan platform, camera, a good point to turn, and without the spacecraft having to turn. Scan platform. I was lucky enough to get invited to join the Voyager team back in about 1978, before we got to Saturn, because there weren't any ring experts around on the team at that time, so they invited me to join. So I kind of organized most of the rings planning for Voyager through Saturn, Uranus, Neptune. And just in case some of you younger people don't have an idea as to what 45 years will do to a guy, that's what 45 years will do to a guy.
That's your grandfather?
No, I'm his grandfather. No, that's me back in 1980. So we were actually designing Cassini while Voyager was still flying. And Cassini was approved in 1990 by Congress. It's a much bigger spacecraft, as you can see from the people down here. And it's got the size of a good-sized RV. Costs about the total cost of Cassini, run-out cost, spacecraft, launch vehicle, 13 years of Saturn was about just a little bit less than $4 billion. Okay, so that works out to about $2 per year per American taxpayer. So you're all taxpayers, you bought it, and you should get a chance to enjoy it. So I hope you will. Some of the experiments, these were jointly done with the European Space Agency. They provided the probe. This probe is actually a thing that flies down through Titan's atmosphere. I'll show you all about that later. That was provided by Europe. And the various experiments. Here's the cameras were all mounted right on the spacecraft. I'm going to talk about this dust analyzer, which measures tiny particles outside the system. It's the power sources. They've got little plutonium golf balls, and some of you may remember there was a big fuss about this way back when Cassini was launched. So I had the opportunity to get involved with some of that too. So there we were at the Cape, October 1997. Big giant Atlas liquid fuel rocket, 2 solid fuel boosters. Inside this thing is another liquid fuel thing called the Centaur, secondary launch vehicle, and Cassini sitting up on top. So that's the whole stack. And it was a beautiful nighttime launch. Off we go. From Florida, Cape Kennedy. Yeah. This was actually from the Air Force launch pad out there. So we could only get within a couple miles, but it was still pretty spectacular. In Florida. Cape, used to call it Cape Canaveral.
Okay. And they do again.
Oh, do they again? They changed. I thought that might be.
Space Center is the Kennedy Space Center.
I always like that name better. So. Oh yeah, sorry. I want to talk about the tour. Hold on. Oh, this thing doesn't go back. Oh, maybe it does. Oh no, it just goes forward. Well, all right. Hold it. Okay, I was going to show you the tour. Hold it. That can't be.
Page up, maybe.
No, let me think. Oh, here we go. This little thing. No, we'll go back. Okay.
Is the back page up or left?
No, I don't think it's just going to let me. I'm going to restart this here. Hold it. Okay, where am I? Because I want to show the tour. There we go. Okay. All right, here we go. Play. Boy, I've never done it this way before, and it's, okay, where's my cursor? Play. Nope. Where's the cursor? Oh, here we go. All right, record and play. All right, so here we are. We're back with the tour. Launch from here, 1997, inwards towards Venus, past Venus. pass Venus again, pass the Earth, pass Jupiter. Every time you pass one of these planets, you get a gravity boost. So you're going, 15,000 miles an hour by the time you get to Saturn. We get to Saturn in about 7 years. Got to be very careful because this is a one-way show here. Turn the spacecraft around, fire the retro rockets, slow us down, put us in orbit. Saturn orbit insertion right over the rings. And then we went into a big, long, loopy orbit, first of many. Uh-oh, okay. Well, that went back. And about a year and a half later, the spacecraft dropped the probe, and it went down into the atmosphere of Titan. Took about 2.5 hours down on parachute, making measurements all the way down, and ended up on the ground. Also took some pictures on the way down. And these are the highest resolution pictures we have of the surface of Titan. On Titan, it's so cold, the mountains are all ice, water ice. And through these mountains, as you can see, these are obviously rivers, more rivers. So what is it that can flow like a liquid on the surface of a body that's, 200, 300 degrees below 0 centigrade? It's probably something like gasoline. And where that gasoline is made, it's in the atmosphere of Titan. I'll talk a little bit about that chemistry later. So Titan is a place where chemistry in the atmosphere produces rain and rivers of gasoline, and they flow down into this lowland, whatever it is, and they actually flow in the lakes. And the probe went down and landed right about there. This scale here is about the size of from San Francisco to San Mateo. So it's like coming down, looking at the peninsula on your way down in an airplane. Pretty amazing. And then we ended up on the ground. These boulders here, got a lot of pictures like this, because nothing is moving. These things are about 5 or 6 centimeters across, and they're ice boulders, because ice is the rock. The whole surface is mostly ice. The rock is all buried way down more deeply. So I'll show some more of those pictures later on. So that was the first phase of the mission. That was the ESA phase of the mission. Get in orbit, drop the probe goes down, now we're done. And now we move to the next phase of the orbit of the mission, which is what we call the orbital tour. So this ball of spaghetti here is a trajectory of the spacecraft. We went through 294 orbits over the 13 years we were there. And as you can see, every one of these orbits is in a little different direction. And what's the point of that? The point of that is you want to look at the rings and the planet and the satellites from a whole bunch of different directions. You don't always want to be looking at them in the same direction as the moon. You want to be looking at them from the side the sun is shining on, you want to look at them from below, sun in front, sun behind, because all those different directions, the way the light is scattered tells you about the size of the particles and what they're made of. Right, so looking at this thing in 3D is really important. So 13 years, all these tours, and the way we did this, Titan is massive enough so every time you fly by Titan, you get a gravitational sweep, and it can change your orbit. Little moons can't do that, not enough gravity. But with Titan, you can go to orbits. So that was all that had to be planned. So we planned most of that before the mission. Now this is just to remind you that Saturn itself is just a ball of gas. You don't see anything solid on Saturn. What you see here is a little storm going by, with various jet streams in the atmosphere. Storm coming and goes every now and then with different rates. So it's what it is, big old ball of gas.
Jeff, is that an actual photo?
It's a movie. This is a Cassini movie. What we do is it is taken from way far away, just when the geometry of everything wasn't changing very much. And so everything was just sitting there. Just take a picture every now and then, maybe every hour. Oh, it's real. Yeah. It's a time lapse. Well, yeah, I guess you could say it's time lapse. Yeah, time lapse movie. Okay, so here's another beautiful picture of Saturn. This was an effect that was never seen before. This whole blue northern hemisphere of Saturn. Never known. Never known. Not from Hubble, not from Voyager. Good question, why? And with the rings, a couple things I want to point out from this picture. One is that the rings in many places are not opaque. Like here, see the rings are semi-transparent. You can kind of see through in places. Then there are other places where the rings are totally opaque. This is the B ring, this is the A ring, and I'll show other pictures to give you this idea. Down in here is the C ring, which is just pretty transparent. The blueness is mostly part of the northern hemisphere of the planet that was being shadowed by the rings. These are the shadows of the rings on the atmosphere of the planet. And it's thought that this shadowing caused the aerosol haze particles, which are yellowish, to sink down. And what you saw was blue sky, okay? Clear blue sky, just like Earth. Only this goes away when the sun comes up and starts creating aerosols.
Hello, can I be heard?
Wasn't ever seen. And the head of the imaging team didn't want to believe it was true for probably about 6 months. But it's a beautiful picture anyway. Here's another beautiful picture. I love this one. Here, this one was taken also when the sun is down and to the right, shining up through the rings over here, casting shadows of the rings on the planet. But the spacecraft is in the plane of the ring, in its own orbit. The spacecraft is now looking right in the plane of the ring. You can see it almost goes away because the rings are very flat. So the sun is not in the plane of the ring, but the spacecraft is. And here you can kind of see that blueness is sort of fade. This little thing is the little moon Enceladus. Again, it gives you an idea how tiny it is. And you can kind of see, how this is a different kind of a picture. This was taken by a different instrument on board the spacecraft that takes images in the near infrared. And so what you see is in 3 sort of filters, maybe 2 microns, 3 microns, and 5 microns, which are like 10 times the wavelength of visible light. And over here you're seeing reflected sunlight, and this, of course, is the dark side of Saturn. It's glowing with heat from inside the planet. That's what we're seeing at the longest wavelength. That's why it's red. So here we're seeing all this kind of cloud structure deep down in the atmosphere, glowing with red light just coming right up in here. It's shadows, it's rays, of course. So that's kind of cool. This heat is sort of left over from the formation of Saturn. Here's another nice one. Just shows sort of the pole. And again, heat escaping from the planet. The rings, because of the wavelengths that they're using here, are blue because water ice absorbs both of these 2 other colors. So that's why we know the rings are mostly water ice and the planet is gas.
Yeah?
Yeah.
Okay, I'm going to tell you about this stuff. How did that picture get taken? I mean,
Well, it was taken far enough away that this particular instrument has to kind of scan across the planet. So the geometry wasn't changing very fast.
it was taken from Earth?
Oh, no, this is Cassini. All you're seeing is Cassini.
Okay, yeah.
Guess what? Do you think you could never see this picture from Earth?
Yeah.
That's one of the great things about being in all these different orbits, right? Because you get to see scenes and geometries that you never, ever would see from Earth. Very important. And here's a big polar hurricane on Saturn. It's about 300 kilometers across. I want to make sure I'm getting, I got to speed it up here. Okay, now I want to turn to the rings. This is a beautiful color picture that just shows all the ring structure, more detailed than we ever saw with Voyager. The C ring, again, the innermost ring. This is this nice, neat, regular bands. The B ring has all this very irregular structure. This is called Cassini's division. People used to think it was empty. At one point, there was some talk about flying Voyager through the Cassini division. Good thing we didn't. And this is called the A ring out here, and I'm going to show you close-ups of all these other things. But you might be able to tell there's kind of a tan color to this thing, and that's because the rings are not pure water ice. And that's going to be a theme that I'll return to again. This gives you a better idea. Now we're looking at the rings from what? The side of the rings that's not lit by the sun. The sun's on the other side of the ring, and we're seeing light that makes it through the ring in our direction. So this tells you right off the bat, well, this is where all the stuff is. The V ring. This is like opaque here, less opaque, even less opaque, lots of light getting through there. So this is a good example of, so this is really where all the mass is, but not the area. Okay, what about the rings? Maybe I will just to say a few things about it. When you look at the rings edge on, they're very, very flat, as I showed you that picture, but they're much flatter. The particles are, for some reason, some things are chopped this way. Particles in the rings are only centimeters to a few meters in size. We knew this before the spacecraft got there. And they just kind of bounce around and collide with each other. And all their very gentle motions, it's like being molecules in a liquid. So just like in a liquid, there's pressure and there's viscosity. And when we explain all these structures, we use the equations of fluid dynamics, pressure, viscosity, and so on. And that's because the particles are just like little molecules. But I'm not going to get into that. But they are about that big, and they bump around, and the thickness is only a few times the size of the biggest particle, so maybe only 30 meters. Okay, that's the thickness of these rings, as we understand it today. Now, okay, this one is a little weird. Too bad. What happened here?
Click on the play button.
Play. There's a play button, huh? This is a little bit odd. Maybe I shouldn't be. I'm going to exit this. I didn't have this problem before, so let me get back out of this. Stop recording. Get into the. Just going to play it right from scratch. Okay. Let's see. This has worked a dozen times. Okay, so there we go. All right, so I said that gravity is sort of important because you're in space now, right? Like up in the shuttle, zero gravity, things float around in the rings because there's so little gravity here, even the tiny gravity between the particles in the rings can pull them together into these clumps. And what you're seeing here is looking down on the rings in a very, very tiny patch. The particles are being pulled together by their own gravity. Then they get torn and stretched apart by the fact that the ones closer to Saturn are moving faster. The ones further from Saturn are moving slower, so you stretch and torn apart. So there's this constant interplay between gravity and stretch. We call these things self-gravity weights that disappeared off the top. And we can study them with this technique from Cuzzi called stellar occultation. The star goes behind the rings. See, here's the star. Lot of star getting through, no star getting through, it's very opaque here. Depending on the angle that the star goes through, you can actually make out the directionality of these weights and tell something about the gravity and the mass of the local rings. So we have hundreds of occultations by stars, by the rings of stars, and I'll show you some more of that occultation data. Here's a picture of the outer edge of the A ring. This thing is called the anti-gap. It's got some little arcs in it. This thing is called the theta gap. I'm going to, it's called the F ring. I'll talk more about those. This little box, I'm going to enlarge on the next slide. You see these little patterns here. These things are called spiral density waves. And these things are like watch springs. They're wrapped spirals, and the physics is the same as in the arms of spiral galaxies. Only they're much more tightly wrapped. So, that's a spiral. And there's gravity waves, so that they're caused by remote satellites just tweaking the orbits of these particles a little bit, and then that gravity just propagates. So this is an image. You can see each one of these is at one of what we call a resonance, which is when the orbit time of these particles resonates with the orbit time of a particular moon. And that's what drives these waves. I mean, you can actually look at them with these stellar occultations and amazing detail. And we learn about the mass of the material that they're propagating through. So that's how we learn what the mass of the rings is. In one way, we can measure the mass by this wave that propagates through it by virtue of this effect. But as I say, the B ring here, this is the puzzle we had. There's no spiral density rings in here. You can't see them. So we didn't know the mass of the B ring. This turns out to be a problem, which I will get to at the end. Okay, so here we go. A couple little movements. This is what these movements look like. This Enki gap. There's a little movement in here called Pan. Here's a close-up of Pan. This thing is called Atlas. It's out here somewhere in the picture. These things look kind of odd because they're big. I mean, the rings are only 100 meters thick, right? And yet there's a movement in here that's 10 kilometers in size. So what happens when that ring material ends up on the moon? It forms this little skirt around the equator. And that's it kind of reminds people of this kind of, it makes you hungry sometimes. I don't know, does anybody know what these are called? They look like maybe raviolis, like dumplings or raviolis. Anyway, that's not what they are. That stuff is just ring material piling up around on their surface. Now, I also want to point out from the same picture, just enlarging it, if you look closely here, this picture was taken when the sun was very close to the ring plane, so it's very grazing illumination. And you see this streak and this streak here, these are actually shadows of this ray, this movement here, casting shadow, and that movement there, casting shadow. Can you see those? Those are actually shadows cast on the rings by those movements. Pretty cool. So another thing I want to point out, now we're going to look a little closer at this Enki gap here. And what you see is this ripple on the edge of the ring. And here's another gap with movement, another ripple. This is a computer simulation of what you get, and as if you were just following the movement, and it wasn't moving. And the ring material is coming by this way. And as the ring material goes by, it gets gravitationally pulled by the moon, and it starts to oscillate. So the physics here is just like a rock in a stream. You've probably seen this, right? You have a big boulder in a stream, water's flowing over it. What do you see? You see behind the stream, you see this ripple. Exactly the same physics.
By the way, a little side note, Saturn's rings went head-on about 2-3 weeks ago.
How about that?
Say that again?
And twice every 29 years, it gets head-on so you can see those shadows he was talking about. And that happens to have been in late March.
Missed it.
Can't see it, right?
Yeah.
It's the absence of it.
Yeah.
What about the shape of those shepherd moons? They're so unusual, it's like a big bowl and then like a half rim. Does anybody figure out why?
A big ball and a half.
Well, like a hat.
Oh,
Yeah.
I showed you.
Yeah.
Oh, well, yeah, I think the reason is because the ring material, it's only 100 meters thick. And this, you can tell there's stuff in here. It's just leaking in to some degree from both sides. So as it leaks in, it's in a very, very, very flat layer. But the moon is 10 kilometers. It's a giant mountain.
It picks up a half rim.
Yes,
That's what it's known.
Well, that's what it is. Well, we don't really know, or I don't really know. They probably are. Somewhere.
Because they're so uniform.
Yeah, well, the stuff is probably coming in from both sides. And, but as you say, they probably had a spin. You know, it's not perfect. Remember that picture, you see what the work and distorted too. But that's basically the reason for it.
In which way is that little one like? Is that moving? Or
This one?
Yeah.
Well, yeah, this is, everything's moving. And, but the relative motion is what's important. Okay, so let's say that you're just moving with this moon, then the material closer to Saturn is moving faster, or in this case it's moving downward. So this material is moving downward, passes the rock, you get a ripple. This material is moving slower, so it's going the other way, or the moon is moving past it so you get the ripple on the other side? Good question. So one of the interesting things about having these moonlets is this theory about torques, and what does this tell you about something of a bigger picture here? In the formation of planets in our proto-solar nebula, big planets are believed to have carved out gaps in the disk by what they call torques. That's how they affect that material. And we actually were able to check that theory using the ring data, because we know the width of the gap, we know the size of the moon, and we can check the theory, and it works just fine. So now we can predict when Jupiter will open a gap in the disk around the sun. Okay, the F ring quickly, and I believe I'm running. I'm going to skip this because I'm running a little bit behind. I just want to show you this. This is a very what we call a diffuse ring. It's called the E ring. Just dust, very, very tiny dust particles. Been a mystery for decades. It's a beautiful picture. The lighting geometry in this picture is kind of mind-bending, and if you want to ask me about it later, I'll be happy to go back to the slide. But it's fun to think about all those wires on the slide. It's so dark, but the fact is nobody has really understood why this ring is there, because these tiny little particles should not last very long. So they have to be created all the time. That was a puzzle. No. So this was kind of the answer to the puzzle. This little moon Enceladus, even Voyager knew that it was a little bit weird. It's very bright, white icy surface. You notice that it's only got craters on some parts, and no craters on other parts. And usually to geologists, because it's getting hit all the time and craters are being formed all the time. So what a geologist would say for this is, well, this all must be pretty young, and it kind of looks like glacier kind of flow, right? And so this was a very interesting moon. We wanted to take a good look at it, and it was discovered that, look at that, it's got these jets of stuff coming right out of the South Pole. This is little tiny dust grains and gas come right out of the South Pole. This moon is being heated by tides from Saturn. It's flexing, and it's got an ocean. I'll show you that in a minute. And it's pushing all this dust and gas right out of the pole. Here's another interesting picture. Shows you these glaciers and gas. So that's cool. So now we understand the E-ring. What else do we learn from that? Of course, the spacecraft can fly right through these plumes, and we did on many occasions. And with this dust sensor that we have, we can measure the composition of the particles directly. And it turns out they've got, of course, water. And this is in the gas, but we can measure the gas as well. There's methane, there's water vapor. There's also organic material. Organic material is large molecules of carbon, hydrogen, and so on. Simple organics, complicated organics, carbon dioxide. And the model that has come from this is a ice shell on the surface that's about as thick as our own ocean is deep, and a 65-kilometer deep ocean on the inside of Enceladus, with these boiling from the inside, forcing all this motion. So this is an example of what we call ocean world, and NASA wants to go back and explore some of these ocean worlds someday. But organics, remember, we're producing organic material physically and naturally, not by magic. It's as common in the universe as water ice. Titan has a similar story. Whoops, I can't go back. Yeah, I can. From Voyager, we couldn't see the surface. It was just this haze. We knew that sunlight, ultraviolet light, acting on the methane, we knew it was in Titan's atmosphere, was producing some kind of smog with methane and settling. And we knew that Titan was losing hydrogen, and so we could create these molecules, but we couldn't see through. So now with Cassini, again, with this near-infrared telescope that we have on Cassini, it can look right through the haze and start to detect continents, and there's no liquid water. I'll show you something else later. But remember, we saw rivers. So there's some liquid rain, gasoline rain, making rivers. And so this was what we learned from the flyby imaging. from measuring the mass with gravity as we flew by with the spacecraft, we can actually determine, how big was the ice shell, how big was basically the rocky material is only like yay big. So Titan also has a big subsurface ocean and an ice shell. Okay, so it's another ocean world. So now we've got two ocean worlds at Saturn, both of which have oceans deeper than our own. And we'd sure like to go there someday. So I want to talk a little bit about this. Just be careful, there will be a quiz at the end of the talk on this slide. But basically, for those of you who may be chemists, the idea is this loss of hydrogen is important because the reaction shows that hydrogen actually keeps the reaction from going to these heavy organics, but it's being lost on Titan. No hydrogen, that's how you get the heavy organics. So that's why Titan is so important in this organics story in Unique. Okay, so take home, organics are common, water ice is common in the Saturn system. Now I'm going to just skip over the next two, I think, and you can ask me about the radar later if you like, because I am getting running long, but that's fine. I want to talk about the origin of the rings. That'll be the last thing I talk about here. This is a color enhanced version. Like the first picture I showed you, you saw that the rings had this kind of tan color. But this shows, compared to, again, our friend Enceladus, the purely water ice moon, even in the enhanced version, it's white. So it's very much pure ice, even enhanced. But the rings are quite obviously not, they're red. So why is that? Been a big puzzle. So there's a couple things we want to learn from this. First of all, what is the nature of that red material, the non-icy material? And second, how much of it is in there? Those are the two things we can learn from looking at the rings. So some of the things we do looking with the cameras, this is the highest resolution true color image of the rings. So they're not red really, they're kind of its tan, warmish color. But this actually shows, here's 300 kilometers. So that's 200 miles. It just gives you an idea how big these things are. And if you stretch these, this picture, you find, yes, there really are color variations in and out of these various structures. And we're still doing the modeling of this to try to figure out all that. But what we do have in the meantime is we have radio telescope on the spacecraft. It's actually the communication radio telescope that can actually measure the radio emission from the rings. And this radio waves are so long that they actually kind of penetrate through all the water ice in the rings. And they can tell you how much of this non-icy material there is total in the rings. And it turns out to be less than 1%. So they're 99% water ice, 1% not water ice. And the not water ice is, well, I don't want to give away the story because that's been a big question. Well, what is that red stuff? A lot of people like good old-fashioned rust. Okay? Mars, for instance, is probably some version of rust, hematite. Organic material is also red. Carrots, tomatoes, watermelon, they're red. And these are things, they're due to molecules they call PAHs, polycyclic aromatic hydrocarbons of these carbon rings, and they're red because they absorb in the ultraviolet. So, well, which is it? And each side has their preferences. One other observation that we got during the whole period of the mission, this chart shows, this is the Cassini dust telescope I showed you. And what does that mean? A dust telescope. It's got all these electrical grids in there, and it detects a particle coming through. And they've got multiple grids, so they can even tell you what the direction was of the particle coming through. And they can tell you the mass when it hits the thing down there. So it's a cool telescope. It's not like big. Again, it's a dust telescope. Stuff that falls in is very definitely not water ice. It's 30% carbon, 30% rock. So it's dark stuff, not ice. So really worry about how this stuff can pollute the rings and use that as a way to tell how old the rings are. So how did this thing work? All through this whole ball arm, remember the tour that I showed you? This is kind of what this instrument was doing all through all that tour. And over the tour, they detected like 123 little particles, or about 1 to 20 microns in size. And those particles are shown on this complicated plot. I won't go into it much, but basically you can model their directions, where they're coming from, and compare them with a prediction. And what the prediction tells you is that these guys are coming from what's called the Kuiper belt. It's like the asteroid belt of the outer solar system. Okay, and it's flat, and it's all going around the same direction. So they're not comets, really. They're not cometary. Comets have orbits that go in all directions. These orbits are pretty flat, and they're pretty localized. But the total amount of mass that was also measured, grain by grain, all these 120 grains, it's the second thing that we really needed to know. We needed to know how much was there. I told you it was less than 1%. We need to know how fast it was getting polluted, and now we know. We know what the mass flux is. So we can start using these things as a clock to tell us how old the rings are. Remember, this is just two. We need one more. What's the third one? We need to know how much mass totally is in the rings. We know what fraction is in the rings, but not what the total mass is. So in the later orbits, these are the ring grazing orbits, what we actually brought the spacecraft through the ring plane right outside the rings, and then, you can see there's about a dozen orbits in here. We brought the spacecraft between the rings and the planet. So we did quite a lot of planning about hazards and everything else as we were doing that. And there's amazing things you can do when you're coming this close to the rings and the planet, some of which, but not all of which, are we can measure the mass. How do we do that? The gravity of the rings affecting the orbit of the spacecraft. We can detect the small changes in the orbit due to the gravity of the rings as it comes this close to the rings. So we can measure the mass of the rings directly. So that is now the third thing that we need: the total mass, the rate at which it's being polluted, and how much pollution it's got in it. The other thing that we measure is the composition of this material, because we're kind of going through it. And again, this is like a spectrum of mass. It's Enceladus. These are signatures of organics. Titan. These are signatures of organics. And the rings, signatures of organics. So here's your smoking gun right here. The stuff that's causing the rings to be red is organic material. The rings' mass is too small for them to avoid getting polluted over the age of the system at the rate that we can see they're getting polluted, and still match the amount of pollution we see there today. So here's the answer. So we combine these three very important observations, and we can measure the age of the rings, and it's like 100 to 200 million years. So where does that put you? Sort of around the time that the dinosaurs evolved on the Earth, maybe as far back as the fish. There's uncertainties in all this, but very definitely not as old as the planet itself, which would be, way down below the floor somewhere in the basement. Okay. Planet is 3.5 billion years old, 3.6 billion years old, and we're talking about 200 million years old. So the rings, as Antonio gave the game away, at least there are a couple of scientists in France who remain convinced that the rings are old. So we have our little friendly debate going on. But I think if you actually look at the numbers, it's very hard to avoid that the rings are really this young. So you could say we're lucky. Oh, I did want to. Well, maybe I should wrap up. But and you ask me a question if you want to follow this line of thought. I can talk a little bit about the origin scenarios of the rings. But I think in view of the time, I think I will. So on the last orbit of these series, we came down, and instead of going for another one, we retargeted so that we actually went into the atmosphere of the planet. Why did we do that, you may ask? It was because, well, we were kind of running out of juice on the spacecraft, we were running out of money to run the spacecraft, and you didn't want to just keep randomly flying around the Saturn system because it might land on Enceladus or it might land on Titan. And NASA wants to go back and look at Enceladus and Titan in the future and look for life. It's a long shot, in my opinion, but you don't want to be the one that brought life there in the first place. So that was the reason for burying it good and deep in the atmosphere of the planet. And I think this one, if I can play it, you may have to listen to it from my laptop. It's a nice movie that JPL made. Let's see. Here we go. Can you hear that? Make it louder. Yeah, I love this video. Yeah, suitable end. So becoming part of the planet itself is the way. So I just want to remind everybody that, this mission is, you can tell, it was a big mission. Hundreds of people involved, JPL, engineers, trajectory, thermal, lots of things, plus the scientists, of course. I think I'm seeing this picture somewhere. Anyway, that's it. And if you guys have questions, I'm happy to take them.
Go ahead.
Yeah, go ahead.
Before when you mentioned gasoline, literally gasoline in the car, or that's some generic?
It's a generic interpretation. It would be mostly ethane, because the methane gets created, methane is a gas at Titan temperatures, but ethane is not. Ethane is a liquid. And so ethane falls out of the atmosphere as a liquid, but you saw the quiz, remember the quiz, there's all these higher molecular weight compounds that are acetylene and all these other things, I don't even know their names, and these heavy hydrocarbons would dissolve in the liquid ethane. So that's what we call gasoline, because water, solid.
For the audience, I want to say, raise your hand, and I'll try to be sure to pick you up as well, but go ahead.
You were showing the icy surface of Titan, and then you were showing, was that ethane, an ethane ocean as opposed to water?
That was actually one of the things I skipped over.
What's the question?
The question was in the cross section I showed of Titan. Remember I showed like the rocky core, right?
Mm-hmm.
And then there was the ocean and the shell. Is that what your question was about?
Well, is that ocean ethane or is it water?
Water.
I think it's water.
It's water. But if anybody wants, I can show you some pictures of some lakes that are made of ethane. Maybe we get through the questions, I'll show that.
I think it's pretty interesting that the age of the rings that you have it coincides with one of our mass extinctions. And so the whole thing, the solar system's been going through some changes and happening at the same time, probably.
Well, that's a very interesting point. I should probably say a little bit about what what we believe the cause of this formation of the rings is. It's the thing that caused the extinction of the dinosaurs, as I'm sure everybody knows, is an asteroid coming in and hitting the Earth. And we know these things happen occasionally. There have actually been multiple extinctions.
Oh, yeah.
But that's kind of a global, that's a solar system-wide thing. Like maybe Jupiter stirred up the asteroid belt, or maybe Saturn did. That could happen almost any time. With the rings, I think it's just a coincidence. And the reason is that around Saturn, all these little series of little icy moons, they're all getting evolved away from Saturn, just like our moon evolves away from our Earth by tides. and they hit one of these resonances where they can start to stir each other up. And you can predict when this would have happened. And it seems like it was about 200 million years ago. And so two of the outer moons could have collided with each other. And that rubble, some of that rubble goes flying in towards Saturn and forms the rings. So some of the models actually, there's a couple of things the models explain. One is why are the rings almost so pure ice? Because nothing in the universe, nothing in the solar system is really pure ice, because it's 30% ice, 30% rock, 30% carbon, right? That's what comets are. The primitive basic material, that's what it is. How do you separate out all this water ice? It's like a distillery. How do you distill the water ice? Well, this collision model actually works, because when you get this collision, it's mostly the mantles of these moons that get sent in towards Saturn. So it's a way of separating the ice from the rock. So I like that theory, actually, myself. Again, it's not universally believed. But the timing of that is not physically, causally related to the dinosaur extinction event.
Right, I wouldn't think
But this,
so.
in fact, this was the formation. No, the dinosaur extinction event is at 64 million years, not 200 million years. So, right, two different things.
Right, it's just kind of interesting, and we don't know as a whole what the solar system has gone through.
Right.
But these are a couple of data points that have
Couple
to
data
be
points.
the same.
Right. The take-home message is things are wild and crazy out there, and things change. And you see impacts happening all the time.
I'm curious, what was your biggest surprise that came out of the scene? Either of the theories that you had ahead of time, or just the whole experience? Certainly the public was falling in love with it all the time. And or what's the biggest argument that you might have with people right now that you can't prove it yet?
Okay. Well, let's see. There's so many surprises. I think the Enceladus plumes was a surprise. I was on the young ring side of the ledger before we got there, so that didn't necessarily surprise me so much. But we had to prove it. I'm trying to think what else. The blue North Pole of Saturn, that was a surprise to everybody. A lot of people didn't believe it. And how can that possibly be? And if you think about it a little bit, it's just that, well, it's all photochemistry. Photochemistry causes the orangish look on Titan. Photochemistry on Saturn, similar enough, except for the hydrogen that's there. So if you turn off the lights for a year or more, then a lot of that aerosol stuff just kind of settles down, and all you see is the gas. But in hindsight, it's funny. Once you've been thinking about these things for 15 years, none of it seems strange anymore. But I think that was the thing I remember being very surprised by.
At least there wasn't a hexagon.
Well, yeah, there's a hexagon. Jupiter has one too. So
One of the images you showed about that storm, colorized. Was that colorized? The rose? What they call it, rose?
the polar hurricane. No, that was, well, it's not exactly colorized. It's one of these pictures that they take, and they can take any three wavelengths at any wavelengths and call this one's red, this one's green, this one's blue in color. So it's false color. That's the way I think about it. So the red was a wavelength that sees very deep into the atmosphere. So that red part that you saw is very deep and very low. And so, you actually, it's 100 kilometers deep. And the surrounding material was higher up, because they're looking at wavelengths where the light is more strongly absorbed.
How long?
Next.
Oh, sorry, you pointed at both of us. Sorry.
I think,
If this had been a movie we were watching, there would have been numerous places where things would fail, and then they'd have to reevaluate or limp along, or something tragic would happen. And this thing just worked wonderfully. How did that happen?
you gotta make an investment. Cassini was the last of the old time space missions. In fact, some of you may remember this guy, Dan Golden, who was the administrator of NASA, and his mantra was faster, better, cheaper. And all the engineers were saying behind his back, well, you can have two of those things, but you can't have all three. And that's what it was. Cassini was done the old-fashioned way, and so it was expensive. It cost $4 billion, $2 of your own hard-earned money every year for 13 years. But the way it's expensive is because you do the calculation, and then he checks you, and then I check him, and that's how we avoid making mistakes. Human error happens. And in the faster, better, cheaper mode, well, that's the part we cut out. And so the Mars thing, the crash, there are things that happen when you try to do things faster and cheaper, which you can do, but they're not necessarily going to be better.
It didn't look like it was much protected. All the equipment looked like it was just open to the atmosphere, and as it was flying through, it looked very lovely.
Well, while it's at Saturn, right, it's just, okay. When it's not flying into the atmosphere itself, there's nothing that can really threaten the equipment because it's vacuum, except occasional meteorites. And so we were very careful about where we had flying through the rings. We did a lot of calculations about all that and tried to find the safest places to go through. And fortunately, we were right.
So it wasn't automatic, you were making changes as it was up there?
We could. There were a couple things that went wrong, and the probe had a problem. We had to change some of the orbits to adapt to that. They had a telecommunications problem on the probe, so we had to put things on hold. So some things happened, but generally speaking, it was pretty trouble-free.
But Jupiter has radiation. Saturn, does it have that?
Not as strong as Jupiter's, that's true, and Jupiter's magnetic field and Van Allen belts are much more powerful. Yeah, cook you.
Are you in that picture?
I don't know. I thought, well, there's another one. I mean, this is only a fraction of the picture. It's this big.
Who knows, you might be.
I think he was first.
So what do various models predict for how long they will last?
Okay, so that's a good question. There's another part of the same physics, okay, that allows us to age date the rings. If you extend that forwards, you can ask yourself, well, okay, fine. They're so old and it's still going on as far as we know. How long, or what does that do going forwards? And it does two things. One thing is it will keep making them darker, of course, but it's gone 150 million years and it's only got about 1%. So that's not the major effect. The major effect is that as this stuff falls in on the rings, it acts a little bit like a disc brake. It's taking angular momentum out of the ring particle orbits. So the rings are gradually moving in towards Saturn under the influence of all this infall. And so a colleague of mine at Ames Strata has actually done these models in 100 to 100 million years. So they also won't last too long. So now that raises the question of, well, what about those rings at Neptune, Uranus, and Jupiter? I mean, could they have been originally big massive rings like Saturn? And they're in their end stage right now. They've been eroded and drifted in toward the planet and one thing and another. And it could be.
I mean, the Earth used to have.
Well, we don't know that.
Well, after it was hit by whatever food must have.
Not known. Could have been. I mean, you could speculate, but that ring, if that were, there are different theories about why the pole is tilted. There's a dynamical theory as well. In addition, I don't know. I think people like the dynamical theory instead of the actual direct tilt theory. Certainly at Neptune, there was definitely something there that led to Triton and all that. So yeah, they could have been bigger in rings in the past and have been devolved into the planet. So we understand that now. So we're lucky to be living here right now when we can see Saturn's rings is beautiful. Lucky, you could say, within a window of only 300 or 400 million years. So. Yeah. You could can think of, not quite, as a nuclear thermistor. It was like a thermistor, what do you call that thing where you apply? It was like a thermocouple drip. So basically they put this plutonium-239 in this ceramic, like toilet material, impermeable. And this stuff would just decay, and these little golf balls would get hot. And they put the thermocouple on it. And they generated 650 watts or so for most of the mission. But that was the fuss at the time of launch and Earth flyby, because some people feared that it would blow up on the pad, and all this plutonium, would fly around. The claim was made that if you took, there's some non-trivial amount of plutonium, 44 grams or some amount. There was enough, the argument was made, there's enough plutonium on board to kill everybody on the Earth. And that's like saying there's enough water in the Great Lakes to drown everybody on the Earth. You just got to get it into their lungs.
It's encased in some incredibly hard material.
Yeah,
It's
this is
practically impossible to destroy, even if it came flying through the atmosphere.
Yeah, they're built for that.
There.
But people, so there were some people who, including very famous anti-nuclear activists from the bad old days of the Cold War, who I had respect for what they did at that time, but they were getting a little bit emotional about this one. Yeah, so I talked to a number of the nuclear safety experts, and fortunately, everything worked out fine. And I think I actually wrote a piece that was circulating on the internet for a while about this. Oh boy, they tore into that one, and I just stopped reading. It was like trolls of the day.
So those last orbits where you're going inside the rings,
Yeah.
were there some spectacular images obtained of the rings close in, looking out? Because I haven't seen a lot of published images from that last set of orbits.
Well, I can show you a couple. I wouldn't call them spectacular, but they are. It'll give you an idea of the kind of thing that we saw. Let's see if I can find this. Here we go. Let's see, can you see that? This is a little tiny piece of the C-ring. Remember the C-ring? Those bands in it? This is a teeny tiny piece of one of those bands. And if your eyes are good, you can make out some little streaks in here. And if you play games filtering the picture, they get a little bit more clear. So this is something, this was actually a surprise. I picked this out of an early image, and we actually retargeted some of the images to capture all this. So this was a surprise, these streaks. So I don't think, we still don't really know what it is, but I think everybody's guess is that they're caused by little movements in here, maybe even meters in size, that is clearing out a little lane in there. But then there's some other kind of noise in here. What is all this? So there's actually, I should show you another picture then, which is even more interesting. This we actually got, okay, come on. Okay, this is fast. These, we call these things propellers. So that gives you an idea. This is a model. If you put something in, remember I told you the moonlet could clear a gap? Well, if you put in a smaller moonlet that's not big enough to clear a gap, you get this kind of thing. It's just clearing out a little channel. And these are like orbit diagrams. And what you get is this thing that we call a propeller. Well, if you actually looked at, you can see right there, see? There's about 10,000 of these things in the A-ring. All these things are probably about 100 meters in size, or tens of meters, 30 meters. And they're just what? Rubble from the original fragmentation? We don't know. Or are they somehow grown in place? We don't know. So these are, there's a lot more. But I think the thing about rings is that a lot of the magic and the structure, you don't have to be looking at it with a microscope so much. There's so much that we see, even all the images we got right now, those bands I showed you in the B ring, There were 300 kilometers. Nobody knows what causes those things.
For some reason, this is not showing up in the sharing of the screen.
Oh, I don't know. Let's see.
Some people are on.
Let's see. Where am I?
We're trying to get Dr. Cuzzi to share the images. They're
Oh,
somehow
about the
not coming
Rings of
through.
Saturn. Okay, hold it.
Give us a minute.
Well, it says I'm still sharing. Nobody, do you see the big thing says Peninsula Astronomical Society? No. Oh, stop share, start share. Oh, wow. Let's see, share this screen. How's that?
Yep.
A little better? Okay, so let's get rid of this again. Okay, back to this one. Back to the full screen. Yeah, propellers. There we go. So you see all these little dashes in here. These things are, maybe, I don't know, 50 kilometers long, less than a kilometer wide, 10,000 estimated, maybe 10,006. And they come in, there's 3 bands in the A-ring where we see them concentrated in 3 distinct bands. Why? We don't know. You can see out here, you can see with your own eyes, there's not any of them out here. There's plenty of them in here. So it's variable. Is it rubble or what? We don't know. Fascinating. This is another one of these density waves. This is one of these spiral waves.
Do they cause temperature changes? I mean, is the material interacting with itself so that you sort of heat up a little bit?
Collisions can heat things up, but these collisions between the ring particles are at speeds of less than a centimeter per second. So they're very, very gentle collisions, and they just bounce. So there's not a lot of heat that gets generated there.
You mentioned the Cuzzi division isn't empty, so tell us about it.
Okay. Let's see if I can show you a better picture of the Cuzzi division here. Let's see. Oh yeah, these are the lakes. Well, there's part of the Cuzzi division. So this is a beautiful picture actually because it's also the outer edge of the B ring. And what this is taken around the equinox when, if you're taking pictures, you want vertical relief, you want to get low sun angle. And this is taken at equinox. So these are shadows of whatever stuff is. And we don't know what that stuff is. But it's vertically extended up. It's the ring, a whole ring, which is only, tens of kilometers. I mean, these are big, tall structures. And the ring itself is only, 30 meters thick. So the whole thing is somehow being flapped up right at the outer edge of the B ring, which is this most massive ring. Well, we know there is a resonance with one of the moons, Mimas, that's vaguely associated with this general area, but there's nothing in that theory that would have predicted this. But this is not a very good picture because that's just the inner part of the Cassini division, but I just thought I'd show that. That is, the B ring doesn't have so many, this is just a band in the Cassini division. There's 4 of them. I wish I could, while I'm on these, I'll just show you these lakes. These are lakes, okay. Right on Titan there, we had a radar on board that could see through the atmosphere, and these little things are these gasoline lakes. And they're about as big as Lake Tahoe. And they can measure their depths, and they can do all kinds of things with them. And this stuff up here is this dune field. And so what's the sand of the dunes? It's probably this tar, heavy organic material. If you take frozen tar at 200 degrees below zero, it's going to be like a grain of sand, right? And so blown by winds, here's a terrestrial analog right out there, Arabian Peninsula. Same thing, they call them longitudinal dunes. So what this means is that large parts of Titan are just these deserts of granular, probably organics, getting blown around by Titan's surface pressure is bigger than the surface pressure on the surface of the Earth. Okay, and a little bit, 1.6 bars. But the gravity is so lower, so the density is actually much higher than the density at the surface of the Earth. And there are winds, they're pretty slow, but they can drive things around. Let me see if I can find more of the Cassini division. I'm going to crack out of here. Yeah, let me, not anything like would live on the Earth because the temperatures are so low. There's no liquid water anywhere. Let's see. This Cassini division picture. Oh, well, it's not a very nice picture. Let's see. It's a sea ring. That's a sea ring. Well, okay, these are actually not bad. This is a good one. This kind of makes the point, too. Let's look at the rings on the other side of the planet, the sun on the other side of the rings. So the Cassini area, which is like here, has a structure that's very reminiscent of the sea ring, especially the outer part of the sea ring. The structure of this sort of plain band here is sort of a linear ramp in optical depth of material. You see the same structure here and here. We think that the structure on the inside, the very abrupt inner edge, is a feature of this meteorite bombardment process that can actually be modeled. But in this Cassini division, in addition to this band here, it's got these other, let me see it better out here. There's 1, 2, 3, 4, 5 kind of bands. And these are gap, 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 and a wider gap, and another gap. And I actually thought back at the time of Voyager, we thought that there were movements that were causing these gaps, and we looked very hard to find them, and we didn't find them. And we didn't see them to see them, so they're not there. Even though we did find movements in this gap and this gap, but not these gaps. So I mean, it's a bit of a puzzle as to what causes these gaps. And people have done some numerology on their locations, and it's, there are some irregularities related to the outer edge of the B ring. You can play those numerical games, but nobody really has any physics idea about what's causing it. But it's like another ring. We should call it the Cassini division ring, because it is very much like the sea ring. What's that? When it's a dark matter. When it's dark matter, yeah.
So why was it the blue hemisphere found during Voyager?
Good question. We're from Hubble. Two different reasons. Voyager got to Saturn when the rings were the solar elevation was really low. So the tilt of the rings to the sun was low. So there wasn't this big shadow on either hemisphere. And as we watched Saturn with Cassini over the duration of the mission, of course, we went through equinox, and that blue stuff went away. So it clearly has to do with the shadowing of that atmosphere. Now, why didn't we ever see it from Hubble? Because Hubble was looking at Saturn when the rings were wide open and had shadows and all that kind of stuff. And I think I've actually gone back and carefully looked at that. But I think the answer to that is that the rings kind of block the moon's shadow. Because basically, here's the sun, here's the Earth, there's Saturn out there on the back wall, and we're, can't really. So that's probably why Hubble didn't see it. Okay, I'm lucky I got it this far.
If you want to finish it off.
Oh, I'm finished. Yeah.
Any more questions?
Anybody in the Zoom meeting has any questions? Okay.
Is
So-
there anything else going to go to Saturn?
Well, there's this Firefly mission that's supposed to go to Titan. It's an opticopter, whatever, orthocopter. And that'll be great fun when it goes. It's been delayed, and now, as you're probably reading in the news, who knows what's going to get funded and what's not going to get funded.
I'm sure we can stay a few more minutes, it'll keep us out.
I will stick around, but yeah, you want to formally close it out.
Just want to say thank you so much again for the talk. Let me,
So